Okay, so welcome to the third day's talks. The first talk is by Srikanth Iyengar. We'll continue with duality and stratification in commutative algebra.
Thank you. So this talk is also going to be sort of on the same topic of approximations that I discussed last time. And this is sort of a working title for this lecture. And I chose this because there are two results from this paper that I want to present, or rather two results that get discussed in this paper that I want to present. That will be the highlight of this lecture. And this paper is due to Amnon Niemann from 1992. Okay, but let me sort of go back and revisit some definitions I should have made maybe last time. So let's say T is any triangulated category. And that admits or has all coproducts. So eventually, I will focus on the case where you're looking at the derived category of a ring that we looked at last time. But you might also, if you wish, look at the derived category of quasi-coherent sheaves on a scheme X, or the homotopy category of spectra, or maybe the category that Henning mentioned in passing last time, or yesterday's lecture, the stable module category of a finite group. So all these are categories with triangulated categories, and they all are, they have coproducts, and anything that I say in the beginning would apply to these categories as well. And in some sense, the derived category of a commutative ring is some sort of a toy model for these two. There is extra structure in all these categories. They all have a tensor product. In what I'm saying today, and that is important in the story, but for what I'm saying today, it won't be so important. Okay, so in this context, if you're given a subcategory S is T, I guess I should try and stick to the same font. T is thick if it has satisfies the following conditions. So the first thing is it should be a triangulated subcategory. So if you have a triangle, and if any two of X, Y, or Z are in S, so is the third one. So it has a 2 out of 3 property. Any two of X, Y, Z in S implies all 3 in X. Okay. The next condition is that, oh, by the way, when I say subcategory, I do mean that it's full, and that it's at least it's non-empty, so it will have 0. Let's say 0 belongs to it. So the next thing is that it should be closed under retracts. So if X plus Y is in S, it implies both X, of course, both X and Y are in S. And the last condition is that it should be closed under finite sums. Don't hesitate to interrupt if you have questions. So this is what a thick subcategory is. And if you replace finite by, if you replace all coproducts, you get the definition of a localizing subcategory. So the only difference between a localizing and a thick subcategory is that in localizing subcategories, you allow infinite sums. Potentially, you allow all sums, whereas in a thick subcategory, you only allow finite sums. And these subcategories are ubiquitous. So given, for example, if you're given any exact functor of triangulated categories, then the kernel is thick. And modulo some set theoretic issues, every thick subcategory arises this way because you can take quotients. Okay, so this explains why one cares about thick subcategories. These are kernels of exact functors. Now given so here's the definition, given We already encountered this last time. I want to look at, this will be the smallest thick subcategory containing X. And you can also look at, so I'll think of these objects as being finitely built by X. Finitely built by X. And you can also look at the localizing subcategory generated by X, which is the same thing where you allow replace thick by localizing. So replace this by this. And I'll talk of these as things that are built by X. So starting with an object, you can see what's the smallest thick, what are all the objects you can construct out of that using the operations in the triangulated category, namely taking finite sums, retracts, and closing up under triangles. Okay.
Excuse me. So I think this 2 implies 3 will also imply the third, that it is closed under finite sum, right?
Yes. So I did not, these are not optimal. I said it because I was lazy, then I could now quietly replace finite by infinite and get localizing. So these are not optimal by any means. You're right. So let me give you 2 examples. So if you look at, now go back to dr. So by the way, whenever I write dr, I do mean that R will be some commutative Noetherian ring. Okay, so the first thing is, if you look at what you can build out of starting with R itself, and this came up already last time, these are precisely the perfect complexes. So these are complexes which are these are quasi-isomorphic to complexes of this kind, where each of these is a finitely generated projective. You know, first of all, you can start with a ring. So you're allowed finite sums. So you get finite free modules. And since you're allowed to take direct summands of things, you end up with all finitely generated projectives. And then since you're allowed to take mapping cones, you can construct finite complexes built out of finitely generated projectives. And if you look, I'm in the triangulated context. So Serre subcategories typically one talks of in the abelian context. So this I'm talking about in the triangulated context. This is, maybe you can think of it maybe as the analog of that, the triangulated context. Am I? So, and then lock here, and oops, D of R, and this is nothing but the statement that every complex has a projective, every object, every complex has a projective resolution. So, okay. So the second example, again in the same context, is if you look at an ideal. So if you look at an ideal I, then we sort of discussed this last time. If you look at the objects that are built out of R mod I, the residue ring, these will be all complexes such that if you look at the local cohomology, so, you know, this is basically in the language that I introduced last time, these are basically the R mod I cellular objects. And as I said, since it's a finitely generated thing, it corresponds to looking at complexes whose local cohomology supported on the closed subset is exactly, so is equal to this. This is the condition. And you can reinterpret this condition to mean that if you look at the homology groups, this is basically saying that the cellular approximation of R mod I of M with respect to R mod I is M itself. And you can detect this property by just looking at the homology modules. So this condition This is equivalent to the condition that if you look at the homology modules, these are all supported on I. So is H of I of M for all I, or if you wish, equivalently, the support of M of all these homology modules is in the closed set. So there are various ways you can understand the objects in the localizing subcategory generated by R mod I. So basically, these are all the complexes which are supported on the closed subset defined by I, right? Okay, now, on the other hand, this is a much more complicated thing. And I don't know an intrinsic description of this as a description like this is more complicated. What I mean is, if I give you an R complex, can you tell, right, or can you tell just by looking at that complex and maybe in any of these terms, whether it is finitely built out of R mod I? And I think that's not possible, or at least I don't know how to do it in general. But here's an exercise which is worth doing. So suppose R mod I is regular, has a ring. Right? Suppose a quotient ring is regular. For example, it might be a field. So for example, if I is a maximal ideal, I a maximal ideal, then R mod I would be a field, which is definitely a regular ring. Then there's a very similar description. Then this R mod thick subcategory generated by R mod I is precisely the finitely generated modules supported, complexes supported on I, things in dB mod R. Supported on I. So this is, you're looking puzzled, John? So I'm assuming that R mod I is regular and I'm working in D of R. So the expert should tell me if I'm making a mistake, but I think this is correct. And this is an exercise worth doing. And okay. Any questions? So this is just to give you a feeling for these thick subcategories and localizing subcategories. And the basic question that comes up, and that you want to answer, this is what I've been alluding to, is so when can you tell? So given so fix X in the derived category, given a Y, can you tell if Y is in the localizing subcategory generated by X, and similarly for the thick subcategory generated by X? Can you tell? Can you find how can you tell if Y is built out of X or but even more finitely built out of X? Okay. And the reason you might care for to answer this question is that if, for instance, if Y is finitely built out of X, so it inherits some of the properties of X. So for instance, if say X is perfect, then Y is also perfect. Anything is also perfect. Okay, and there's there are a whole lot of properties of X that get inherited by Y, but of course not everything. For instance, if X is projective, it wouldn't mean Y is projective. So modulo that caveat, properties of X are inherited by Y, which is one reason you might want to answer this question as to whether Y is built out of X or not, finitely or otherwise. Okay. So, of course, if Y is finitely built out of X, it's also built out of X. Sometimes the converse is true, and I want to explain that. Any comments or questions? Okay, so clearly, y in thick X implies y then log X. And there's an interesting context in which the converse is true. And that has to do with compactness. So let's say an object C in the triangulated category T, now T can be any triangulated category with coproducts, is compact or small or compact if for all objects Xi, any family, the induced map is a natural map from, so map from Xi to the sum induces a map like so. You get such an induced map, and you want this to be bijective. So if this holds for any families Xi, then C is said to be small or compact. So
can I ask a question about this log R mod I or thick R mod I?
yes.
Hello?
Yeah, go ahead, Manoj.
So this, I mean, this condition that this R gamma V of I M is quasi-isomorphic to
M.
M.
Yeah.
That is saying that on the complement of V of I in spec R, the sheaf has no higher homology?
It has nothing. It's supported completely on I. So if you localize at primes that are not supported on I, which don't contain I, this will be 0.
The homology, okay. Okay, thanks. Yeah.
Okay, so let me write EC for the compact objects or small objects in T. So by the way, you should check that this is a thick subcategory. So compactness or smallness is also something that gets inherited by things that are finitely built out of things. Okay, so if you look at the derived category, then the compact objects here are precisely the perfect complexes. Okay, and in the geometric context, what you would get is bounded complexes of locally free sheaves. If you look instead on I think maybe Henning will discuss this. If you look at the stable category of a Artin Gorenstein algebra, or maybe I should do that, an Artin Gorenstein algebra, or any Gorenstein algebra actually, then the compact objects are precisely the subcategory generated by the finitely generated modules, like Gorenstein projective modules. And what else? So anyway, these are two examples, and of course, I'll be focusing on the case of a commutative ring. So the result I wanted to mention, and this theorem, is that if C and D are compact, then if C is in the localizing subcategory generated by D, then C is actually already finitely built by D. So if you want, so you don't have to, so finiteness is for free. As soon as you know that this is built out of D, it has to be finitely built out of D. And you can sort of see why compactness might come in, because here you're allowing for infinite sums, but what this says is that any map from C to an infinite sum factors through a finite sum. It seems reasonable. And once again, this is one of those results. Attribution depends on who you ask. I learned it from a paper of Niemann, but I suspect it had been known before that. Okay. Okay. All right. There you go. Okay, so the reason this is useful, so the reason this is extremely useful is that, as already we saw in that example, it's much easier to understand. Often it's much easier to understand the localizing subcategory generated by objects rather than the things that are finitely built or things that are finitely built. Okay. So this is as much as I want to say about the general context. Now I'll focus on the derived category of a commutative ring and get to these results in Niemann's paper. Okay, so this begins part 2. Okay, so I have to introduce, at this point, I need to introduce the notion of support. I already did for things in the bounded derived category, but now I need it for general complexes. So if you're given a point in spec R, I will write Kp for the residue field of R localized at P, of the local ring at P, namely Rp or PRP, which is the same as the field of fractions of the domain R mod P. All right. So then the support of an R complex M is by definition the primes in the spectrum, such that when you look at, you can think of this as the stock of M over P, but this should be non-zero. So you're looking at the derived tensor product of M with the residue field, and that should be non-zero. Good. Very good, very good. That's an excellent question. I ask you to think about examples. So you do need both things to be compact. I think it's not good enough that one of them is compact. I think there are counter examples. That's a very good question. Yes. So what was I saying? Yes, this is sometimes called the small support, but this is the only support I'll use. So the small support. Okay, so let me make a few comments about this. So the first thing is that the most basic property about the support. So maybe I should, okay, let me start with the following. Suppose M is in dB mod R. Then this is the same invariant that I introduced last time. Namely, the support of M is precisely the support of the homology module is non-zero, so which is the closed subset defined by the annihilator of the homology module. So in particular, it's a closed subset. But in general, of course, the support need not be closed. So for instance, the support of the residue field itself is just the point P. So this is also a sort of an exercise one should do. So if you just look at this residue field at P, it's supported precisely at P. And then when I tell you that support of an arbitrary sum is the union of the supports, you'll see immediately that any subset of spec R can be realized as the support of some complex. Obviously, it will not be a finitely generated complex, but of something. And there are various other things I can say about supports. Yeah, so I wanted to mention one important thing. The most important property, as far as what I'm going to say next, is that support detects when things are zero or not. If and only if M is zero in the derived category. Namely, the homology of M is zero. Okay. And So these are all fairly straightforward. This isn't. And what is behind this? So 4 follows from, or 4 can be deduced from the following result, that let's look at the things that are built from M. Those coincide with the things that are built from the stocks. So P in spec H. So both directions are sort of non-trivial. So it's saying, first of all, that these stock complexes can be built out of M itself in the triangulated category sense, which is not too hard, but it's something worth thinking through. And sort of the meat of this is that M can be reconstructed using the operations of the triangulated category from these. Now notice that these are just vector spaces, one for each prime P. It's sort of interesting that you can reconstruct M, the entire complex, from this. But of course, what is going on is that you're using mapping cones and you're using the morphisms in the triangulated category. So I think of this, and not only me, others think of this as a kind of local to global principle. A local to global principle in this context. So namely that you can reconstruct M from this strata supported at each prime P. Okay? Any questions before I move on? Oh, the derived category, yeah. Oh, yes, go ahead. Sorry, Dipendra. Yeah, maybe, yes. Yeah, it's just the derived tensor product. So there are other properties of support, for example, that are handy. For example, right, this is what I should, good. This is what I wanted to mention, that this again illustrates this fact that if N is built out of M, this implies that the support of N is contained in the support of M. So this is again what I mentioned earlier, that things that built out of M inherit properties of M. And this is one manifestation of that. Okay, so I can now state the result. This is due to Hopkins from 1986 or so, I think. And the result is that if you take two perfect complexes, so F and G perfect, and if the support of one is contained in the other, then F is actually finitely built out of G. So this is Hopkins's theorem. Okay, and notice that of course the converse is true from what I said earlier. If F is built out of G, the support of F has to be in the support of G. So this gives you a strong converse. And this is the kind of thing I was asking for earlier, some intrinsic condition or some simple criteria which would tell me when one thing is finitely built out of the other. And Hopkins's theorem says that just this, the topological data of the support of F, the support gives you is good enough in this context. Of course, the key thing is that F and G have to be perfect. Let me sketch a proof. Oh, perfect means that it's equivalent to a bounded complex of finitely generated projective modules. Yep, everywhere. Yes, I was going, yeah, I said that R is always commutative Noetherian. What? I'm taking all the primes. So you look at, yeah, log of the set. So you look at the collection of stocks complexes. So one at each prime, all the primes. Yeah.
Log of the set means
Yeah, it's good. I didn't define this, but it's the localizing subcategory generated by. I could have taken the direct sum and gotten away with. Okay, so here's a proof. Okay, so let's say V is the support. So remember, this is a closed set because G is perfect. Then the support of F being in side V, which is a hypothesis, implies that if you look at the local cohomology of F supported on V, this is F. That we already discussed last time. This is the cellular approximation of F. So it's the G cellular approximation of F because V is the support of G, i.e., and since F is equal to its cellular approximation, it tells me that F is an log of G. So far I've not used anything about F and G being perfect, only that they are finite, only that G has close support. But now, because F and G are compact, that result I mentioned earlier implies that F must be in thick G. And the task for the audience is to tell me what's going on. Why is this even a theorem? Obviously, I've hidden some non-trivial fact somewhere. Where is it hidden? Well, I erase the board. If you know the answer, don't say it. I'm only referring to the experts. No, that's the hypothesis. Hopkins' theorem is about compact objects. Perfect complexes are compact. Any answers? I've hidden something. I told you a story, but I didn't quite justify one step in the story. Any guesses? I open it up even to the experts. Clearly, if this was all there was to it, Hopkins' name wouldn't be attached to it. Trouble is this. How do I know this? So last time I glibly stated that if you take something in dB, then this is the cellular approximation. But justifying this takes effort. And that's more or less what will come next, but I'll talk about this. So this is the non-trivial thing. By the way, this was not Hopkins' approach. As the topologists in the audience know, Hopkins' approach was something quite different, using the tensor nilpotence theorem and things like that. Maybe I'll present it at some point, but this is a different perspective on this result, right? From this idea of looking at supports. And I'll get back to this. I want to, before checking this is closely connected with Niemann's extension of Hopkins' theorem, which I will explain in a few minutes. But before I go there, I want to try and at least give some indication of the power of this statement here. At least I'll tell you the first result that I could prove using this, which got me excited about this topic. So here's an application of sorts. It's not really a sort of a stellar application, but it's anyway, this argument is what drove home to me how striking that result is. By the way, I should say something. All the result tells you is that you can build F out of G, but it's not constructive. It doesn't tell you how to build F out of G. And I'll speak to that later, maybe later in the talk, but that sort of, you can look at that from the result of Dwyer and Greenlees that I discussed last time. At least it gives you one way of trying to understand that construction. Okay, one application. So let's say we have a map of commutative rings, commutative Noetherian rings. And let's say I'm going to try and keep it as context as simple as possible. Let's say it's a finite map. And let's say that N is a complex of in dB. You can even take it to be a finitely generated module, but I'll have to work with complexes anyway. So suppose you know that the projective dimension of S over R is finite, and that the projective dimension of N over S is finite. This certainly implies that the projective dimension of N over R is finite. This is something you'll see already in Karta and Eilenberg, right? So by the way, I'm writing projected dimension just to have, this is the same as saying in this context, this is the same as saying S is perfect as an R module, that S has a finite free resolution or a finite projective resolution as an R module. This is saying N has a finite projective resolution as an S module. And then the conclusion is that somehow it's associative, it's transitive. Okay, so I'm looking at the 2 out of 3 properties. Okay, there are 3 conditions here. These 2 imply this. It's, definitely knowing that, I've forgotten G, a projected dimension of R is finite, plus if you know things over R are finite, this in general does not imply that the projected dimension of N over S is finite. What would be a counterexample? What's a counterexample? So this all.
Am I also allowed to answer?
What? What do you say?
So can I also answer this question?
Yes, of course. Yeah.
You take R to be a nice normalization. I mean, take S to be some non-regular ring and R to be a nice normalization.
You could take R to be a field.
Of course, yes.
You could take R to be a field. These are trivially true, but of course, not every module over a finite dimensional algebra would be a finite projective dimension. But you're right, Manoj. This is what it is. Somehow, interestingly enough, so let me call it a theorem because it's not immediately obvious. The other, so if N has finite projective dimension over R and S, then the projective dimension of this S over R must be finite. Of course, it can't be true in overall. It depends on the support of N, on the support of N over S. Meaning, if you look at a prime ideal in the support, then and you look at the induced. So look at SQ viewed as a module over RQ contracted to R. This is so this would be finite projective dimension over this. So somehow you have this, knowing that N has finite projective dimension both over R and S forces this to have finite projective dimension. And I invite you to try and prove this without using Hopkins. And in fact, I first proved this using some very complicated argument. This, at least as far as I know, it first appears in a paper that Foxby and I wrote in 2000s, but then a year later, I went to Sheffield as a postdoc with John Greenlees, and I learned about that result. And this was one of the first applications that was a clean proof of this statement, which really told you what was going on. So let me sketch the argument, because at least this gives you one indication of how one can use Hopkins's theorem. So you can quickly, since the statement is really local, you can assume the case where this is a local ring, a local map of local rings, and N is of course non-zero. right? All right. So we know, so n still is perfect over S. So n is perfect in ds. So this has some support. So let me take, let's say S is equal to S1 to Sn is a generating set for the maximal ideal of S. So this is the maximal ideal of S. Okay, and look at the causal complex. Let me call it K. This is the causal complex on this sequence. So remember, this is the complex, which is the tensor product of these short complexes. And the thing about this complex is that the annihilator of this is the maximal ideal of the homology. So, and of course, the homology itself is non-zero because in degree 0, it's the residue field. So the support of this causal complex is just the closed point. Now, because n was perfect, it's in particular in the bounded derived category of S. So the support is a closed subset of spec S. So it contains M. So Hopkins's theorem, so in particular, this S belongs to the support. So tells you that the causal complex is finitely built out of n, even over S, and in particular over R. In fact, that's all I will need, that it's built out of n over R. But this is by Hopkins. Okay, so what this allows you to do is replace n by k. And after this, you can forget about n and Hopkins. There is this basic standard commutative algebra, but let me go through this motions, go through the steps. So now you can forget about k, so we can assume. So what we know is that, it means in particular that k itself is, so n was small. So this implies, of course, by the restriction, because the restriction functor is exact, it tells you that a k is built out of n, also when viewed as R complexes, right? So n perfect over R implies k is perfect over R. Okay, at this point you can forget about n. So what this does is it reduces to the case where this is just a causal complex on the generating set for the maximal ideal of S. And then, okay, now, so here's the lemma that's useful. So suppose, say, X, or what shall we call it? So let's say X is any X complex. And you pick an element in the maximal ideal of S. So the lemma is that if the causal complex on this element S with coefficients in X is perfect over R, then so is X itself. So this is some sort of a standard argument that you can peel off things using which you build a causal complex. So this one, by the way, this is just by definition, it's the causal complex on this element S insert with X. So as such, one has an exact sequence. One has this exact sequence, and if you apply or K blank, where K is the residue field of R. what we get is that, so we get Tor I. So this exact sequence gives you a long exact sequence in homology. And that exact sequence looks like so. So this will be S. This is actually the connecting map. So it's some plus or minus S.
Is S a single element?
Yes,
Or
S now is a single element. Yeah.
Ah, okay.
Yeah, I did try to write an underline here. Yeah. This is just a single element here. So now, and then you get or K and the causal complex. Okay. So now what happens is the hypothesis was that this is perfect over R. Namely, this is some bounded complex of finitely generated projectives over R. So this means that this is 0 for all I large enough. But that means that this map must be surjective. This map is surjective for all I large enough. We started with something in the bounded derived category of S, and that implies that these are finitely generated S modules. So this is something to check. In fact, because I assume the map itself is finite, X would also be finite over R, but all you need is that X is in the bounded derived category of S. So these are finitely generated S modules, and this map is surjective. So Nakayama's lemma tells you, so Nakayama lemma would tell you that these must be 0 eventually, i.e. X is perfect over X perfect. So of course, here I'm using something else that over a local ring, you can detect perfection by just looking at tensoring with the residue field. You don't have to do that. You can just take, instead of K, you can take any module and then run the same finitely generated module and run the same argument. Okay, so one way or the other, the takeaway is, from this is that if the causal complex or any complex with one element is perfect, then the complex itself had to be perfect. Now, what you had, so at this point, we're basically done because we know that the causal complex on the maximal ideal is perfect. Thus, so we had K, which is the causal complex on Sn and S. So this is perfect over R, but the causal complex, you can think of it as the causal complex on the one element S1 with coefficients in the rest on the causal complex on the rest. Okay, just because this is a tensor product of n things, you can think of it as the first thing tensor with the rest. Yes. And therefore X is perfect. And this is because R is a local ring and X is in the bounded derived category of R. So X has only finitely generated homology modules. So this is something you have to check. It's an argument to make. Oh, so this is eventually 0. So this is surjective, but this is multiplication by S, which is in the maximal ideal. So then Nakayama's lemma tells you that it must be 0. Okay. And what's left is notice is that this causal complex you can think of as the causal complex on this one element with coefficients in this. So this implies that this causal complex is perfect over R. But then you can use the lemma again to peel off one element at a time and deduce that S is perfect over R. So I did compress this argument quite a lot, but let me say that from this point on, this is sort of standard arguments in commutative algebra, and it applies not just to perfection, but all sorts of other homological invariants. And you can run the same sort of arguments to deduce various other such results of this flavor. And if you want to read more about this or You can find it in a paper called Finiteness in the Derived Category of a Local Ring that John Bildweier and I wrote. So that sort of explains this sort of puts this results in some context and explains and gives you some more applications of this result of Hopkins. Okay. Any questions? Yeah, Saran? Because restriction is an exact functor, right? Because you're looking, so if you look at the derived category of, so this is something happening in the derived category of S. You're interested in what's happening here, but you have the restriction functor. That's exact. So, okay. Now, so this is about Hopkins's theorem, and I said it is a remarkable result that you can detect building for perfect complexes only from their support. So here's Neumann's extension or Neumann's result, which applies to now any complexes for any n comma n in P of R. If the support of n is in the support of n, then M must be built out of n. Not finitely built, but just built. Okay, so this is Neumann's result. So the two remarks I'll make is that this is something that Neumann himself observed, that this implies Hopkins. In much the same, so because, let me just talk through this. It's the same argument that I had before. If M and N were perfect complexes, such that the support of one was contained in the other, Neumann's result tells you that one is built out of the other, right? But then since they are compact, they must be finitely built out of, it must be finitely built. So Neumann immediately implies Hopkins. But in fact, Neumann's result is really equivalent to this local to global principle that I mentioned earlier. Local to global. Now, the thing is, maybe let me not cram it here. Let me say it there. So the local to global principle that I enunciated earlier is really another way to view Neumann's result about generation. So why is that? So the support of n contained in the support of n. So this means that for any prime p, for any p, so this is in fact equivalent to the statement that for any p in spec R, if you look at this stock complex, this so is equal to or is contained in this the localizing subcategory generated by this stock complex, right? Either this is 0, in which case there's nothing to prove. If this is non-zero because of this condition. Now you're working over vector spaces because these are both vector spaces over Kp. And if you have two vector spaces or two complexes of vector spaces that are non-zero, they must build each other. So this is basically because Kp is a field. And we know that you can reconstruct M from this. So this tells me, so this we know is contained in log n. So this implies that M is okay. So Neumann's result is really just the local to global principle. It is a local to global principle if you view it this way. And maybe depending on, actually, you should give me some feedback whether you want to see a proof of Neumann or maybe namely the local to global principle or what, depending on what I decide, what feedback I get. I may either discuss this or something else. Maybe Hopkins's argument, original argument. Okay, So this is as much as I wanted to say about this question of when you can build a complex from the other in the commutative ring context. And I think you will hear analogs of this result in, at least in the case of finite groups. I think Henning plans to talk about this, and maybe you'll also hear about it in the context of spectra, which was the original context. Any questions? Okay, in the last 15 minutes or so, I want to try and question. Yes. Yeah. In fact, yeah, that's a very good point. So remember I said that M, wait a minute, what was it? Yeah, that M. So this was one of the implications, right? So the way to prove it is that the residue field is always built out of the ring, because anything is built out of the ring, because this is dr, right? Now tensor with M on both sides. So then you get that. So this direction is not the difficult one. It's the other one that you can reconstruct M from its strata. Okay, good. Okay, so I want to sort of change tack and go back to this result of Dwyer-Greenlees that I was discussing last time. And it is again, it links up to, it gives you another perspective maybe on Hawkins's result. This is why I'm discussing this again. So I'm changing notation a bit. So let's say G is a perfect complex. And you can just assume that it's in fact equal to a bounded complex, is itself a bounded complex of projectives, finitely generated projectives. Okay, and we wanted to look at this endomorphism DGA. So this is the DG. So this is just looking at the complex, Hom complex. Right? And so last time I explained that we have this adjunction that you can go from R to the EOP, where this would be blank, and I can drop the R home because the G is already a projective, but okay, let's leave it there. And then, but here I do need the tensor product. So this we have. So we have this adjunction, and we saw that the co-unit of the adjunction is cellular approximation. So the theorem was that R home E G to M. Oh, I better take the derived. So this is the cellular approximation of G. Right? So this is what we discussed last time. And so what this implies, what this yields is that it implies that, well, it's epsilon more work. This gives you that the derived category of EOP. So this, it actually tells you that this is an embedding. So this is here an embedding. So what you get is an identification of the localizing subcategory generated by G. So the G cellular objects in the derived category. So these are equivalent to, sorry, not the bounded derived category, the full derived category of this DG algebra. And this is something, this point came up earlier. This is precisely the complexes supported on the support of G. So this is a closed subset, and you're looking at the complexes in the derived category supported on the closed subset. So there's an equivalence of categories between those objects and the derived category of E. Gamma. Yeah. This is what it is. Yeah. So this is, suppose you call this V. So you can think of this as basically R gamma V dg ER, which is the V torsion objects in this. So the complexes in R complexes is supported on V. Where? No, this is just, this is the G cell. This is the full thing, yeah. Oh yeah, this is right. This is also, I mean, correct. You can also interpret this as, yeah. But this is what requires a proof, which is what I hid last time. Okay, so I just wanted to point out that this is some sort of derived Morita theory. If you're familiar with Morita theory, this is just some derived Morita theory. Right? Now, okay, so what does it got to do with what does it got to do with Hopkins's theorem? Let me revisit Hopkins's theorem with this on hand. Okay. So back to the context of Hopkins's theorem. So we had F and G, both compact, and the support of one was contained in the support of the other, right? So let's look at this map. E, G, to F. So look at this map, which is in this Dwyer-Greenlee's context. Yeah, Rekha, you have a question? What was that? Oh, so no. So this map is the cellular approximation map was the statement last time, right? Yeah. So this object is cell, and this map is the cellular approximation of M with respect to G. That's what it is. So that's the claim. So I claim that under this hypothesis, this is an equivalence. So if you accept that, this is an equivalence under of course the hypothesis or an isomorphism of isomorphism. Yeah. So why is that good enough? It's because for then, so assume this. What happens is this object is built out of E. So then it's exactly this sort of argument that came up earlier. So this is in the localizing subcategory of E, because after all, this is a module over E. No, just an equivalence under the quasi-isomorphism. Because under this hypothesis. Yes. So I'm trying to say that the content of Hopkins's theorem really is that this is an equivalence, because once you know this is a quasi-isomorphism, so this is what we have to prove. Or this is really what is being asserted, that this is, because once you know this is built out of E, because after all, this is an E module. So if you tensor with G, this will be, of course, this is happening in the derived category of E, but now you land in the derived category of R, right? Like before, and this is F. But then F and G are compact, so once again the same argument. Again, F comma G compact implies F is in G, as Hopkins asserts, right? That's the content. So we really have to prove that this is an equivalence. But we know it's, as Samik already said, we know it's a G equivalence because it is a G cellular approximation. So let's finish it to a cone. Let's Z optimistically for 0. So if you take this, we know that, so this is a G equivalence, i.e., if you look at R home R GZ, this is 0. That's really what the G equivalence tells you, right? So this is coming from Dwyer-Greenlees. So this, we already know that this is the cellular approximation. So this is, by the way, checking that this is a G cellular approximation is also not very hard. It's a few lines, really. Very standard homological computations. Okay, so you end up with this. I want to deduce that Z is 0, but notice that this one, because G is perfect, so in the derived category of ring, the perfect objects are dualizable. This is what this is really saying. Okay, so this is quasi-isomorphic to this one. All right, now I'm going to do a support computation. Coming from here, you know, this one is of course G cellular. So this support, this has support in G. So this is supported in sub G because this is G cellular. The support of F is also contained in the support of G. So what we deduce is that the support of Z is also contained in the support of G. That's just coming from this exact triangle here. This one is G cellular, so its support is in the support of G. The hypothesis said the support of F is in the support of G. And it's an easy thing to check that if you have an exact triangle, the support of the third one is contained in the union of the other two. Support of one is contained in the union of the other two. Now, where? No, not any Z. This is, I want to compute it to a triangle. Yeah, complete to a triangle. Yeah, right. Just complete it to a triangle, you get something like this. Now, let's look at this one. So what is the support of this tensor product? So the support, on the one hand, it better be empty because it's 0. So the support of the tensor product. Can I write G hash? Oh, well, all right. It's this. So that's the empty set. On the other hand, we already brought this up that the support of a tensor product is the intersection of the supports. If I didn't, I should have. It's not very hard. That's very straightforward. Check. So you get, right? You get the intersection. So this is an easy computation, by the way. It's a general statement about supports that, did I not mention this earlier? Maybe not, I forgot. If you take the support of a tensor product, it's the intersection of the supports. This is, yeah. This is quite straightforward. Okay, now the thing is, another not so difficult computation is that the support of this is the same as the support of G. Again, just use the definitions, use the fact that G is perfect so that it's dualizable. So this will be the support of G intersect the support. But look, the support of this was contained in this one. So that's here. So this is the support of. So you deduce that the support of Z is the empty set. So Z must be 0. As is wished. So one can, And so it's really, again, this property that support detects being 0 or not that gives you this argument. So this is, again, the link between the work of Dwyer-Greenlees and Hopkins's result about building. Oh, perfect. Let's stop here. It's okay. Good point to stop.
Any questions?
Yeah, yeah. Interesting. Is that true? So my gut feeling is probably not, but I don't know. Yeah. I'll have to think about it, but I suspect it's not so. By the way, you should let me know what you want to see next time. I have various things I could discuss. I could discuss the proof of the local to global, or I could discuss Hopkins's original proof, or I could go off and do something completely different. Actually, so the thing is, there is another side to this story. I only talked about half of Dwyer-Greenlees. The other half has to do with completions, and that's also a very interesting part of the story. So that's the third item on the agenda on offer. Yes? Yes, you should ask the person sitting next to you. Or the topologist in the audience. Yeah. Oh, well. Is actually anybody talking about the chromatic story in the spectral context? You are. The Hopkins result in the spectral context. Chromatic filtration in the world of spectra. Are you going to present that result? Okay.
Maybe that can be in one of the discussion sessions.
What?
One of the discussion sessions?
Yeah, sure.
Yeah.
Yeah.
No,
Please don't hesitate to ask questions even afterwards. I know this was a bit compressed at places. So I'm happy to elaborate wherever.
Any other questions? If not, let's stand.